Okay, in this presentation we are going to look at the gambler's fallacy phenomenon. So this is very well known in statistics and probability, and I'm going to look at an example of where it came up in history and consider that. The most famous example of the gambler's fallacy occurred in a game of roulette at the Monte Carlo Casino on August 18th, 1913, when the ball fell in black 26 times in a row. So just imagine you're at this roulette table and you've just seen it go black 5 or 6 times in a row. You're thinking, okay, it's going to go red the next time, so I'm going to bet on red. And then it comes up black again. So you're thinking, alright, it has to come up red the next time. And it comes up black again. And you keep doing this until you run out of money because you keep making the same mistake. So what happens is it came up black 26 times in a row, and this ruined a lot of people. So let me read this out. By the way, this is from Wikipedia. This is an extremely uncommon occurrence. The probability of a sequence of either red or black occurring 26 times in a row is about 1 in 66.6 million, assuming the mechanism is unbiased. Gamblers lost millions of francs betting against black, reasoning incorrectly that the streak was causing an imbalance in the randomness of the wheel and that it had to be followed by a long streak of red. So you're just sort of thinking, people were just waiting it out, thinking it's going to go red soon, let's say after 5 or 6 times, and then they were just wrong. It just kept going black 26 times in a row. Okay, then it became red, but everyone was broke at that stage because they were betting on red all along. Anyway, so what we're going to do here is use some packages, statistics packages. I've just previously used the package manager to install StatsBase and statistics. Okay, so I have it all set up. By the way, I'm using a Jupyter notebook and Julia version 1.6.1. So I'm going to call these packages using StatsBase and using statistics there. Okay. Now the key thing we're going to use here is a thing called run length encoding. And this is very useful for looking at sequences to see how many times something is repeated in a row. Okay, so I have a quick example here, but the key thing here is the second is the number of consecutive occurrences of each element. So this is the example that will be used for this command. RLE is the name of the command. So we have a sequence here. 1, 1, 1. Okay, so that's a run of ones, and there's 3 of them. 2, 2. That's a run of twos, and there's 2 of them. We have a run of threes, and there's 4 of them, and then a run of twos, and there are 3 of them. Okay, so let's just run that. So this gives the value that came up for a particular run, and this gives you, that's the first part, and this gives you how many occurrences were in that run. Okay, so it's a sort of way of re-expressing that information in terms of consecutive occurrences. Okay, so 1 came up 3 times in a row, then 2 came up twice, and so on. So what we can do there is just take out the second part of that tuple. That returns a tuple. And I'm particularly interested in this part here. Okay. So this is where we'll get our 26 from if we're sort of modeling the roulette wheel. There we go. So that gives us the runs, the length of the runs in as a vector there. Okay. And we can pick out the maximum. So there was 4. That's the longest run, okay, was 4. A run of 4 consecutive occurrences. Okay, so I think that actually provides the basis of what we're doing. So we'll just sort of continue on here. So let's simulate a roulette wheel. Okay, so colors are red and black. That's a roulette wheel. And red, so this simulates using the indexing here, where we generate a random array with values 1 or 2, and there are 10 occurrences just in this instance just to get started. So this simulates a roulette wheel spinning 10 times. So red, black, black, red, 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 black, red, black. And that's sort of what you sort of may expect if you were at a roulette table. So that's fine. So that just is 10 spins. Okay. Now let's look at that here, because I'm going to be very important here about what I mean shortly. So there's 10 spins, but there were 4 runs. Okay. That's important. So I'm going to talk about everything in terms of runs here. So there were 4 runs for this particular example. Okay. Let's just try it out again. Make it a little bit longer. There we go. Again, the maximum there was 4 runs. Okay. So that's good. Now, what I'm going to do there is just save it all up. And just take out the second part of the tuple. Okay. And I'm going to call that color runs. So that's the runs. There are 10 elements from... There was 10 runs. 2, 3, 3, 1, 3, 2, 1, 2, 1, 2. Okay. So there's 10 runs in that 20 spins. Okay, so we expect that the number of runs would be about half the number of spins. Okay, so now let's expand that out. So we're dealing with 20 there. Now we're going to really increase it here to 100 million. So we're just about to do the same thing here again. N here is 100 million. And there we go. Color runs. Now it's going to take a second because 100 million is a big number. There we go. So what do we get here? So let's just look at our vector here. I won't try and print it. By the way, sorry, you see what I did there? I put the colon there just to actually stop the output being printed. So out of 100 million spins, we get 49 million runs. Okay, that's quite a big vector we're talking about there. Okay, and the length of we could just pick out the length there at that 49,997,615. Okay, so what's the maximum? So we had 100 million spins, okay, which corresponds to 50 million runs approximately. So in this particular instance, the longest run was 25. Now, if we probably increase the number of runs, we'd probably get a larger maximum there, okay? Or increase the number of spins, which would turn into about, whatever. It doesn't really matter. So it's essentially, that's a big number, okay? Now, what's the median number of runs? By the way, this is median here is from the statistics package that I called, okay? And something I forgot to mention is StatsBase is where we get the RLE command. Now, so 2, that makes sense that, 2 runs is, red, black, red, red, black, and so on, okay? Now, that's it. So essentially what we're going to do here is manage our curiosity a bit. See what would the proportion of runs, how many runs were greater than 5? Okay, so out of the 50 million runs, about 3 million were longer than 5. So it's not uncommon to have runs of more greater than 5, greater than equal to 5. Okay, let's try that again. See what that turns out to as a percentage. About 6%. And let's see, same again, what percentage were greater than 10? Greater than or equal to 10. Less than 1%. About 1/5%. What percentage were greater than 20? Very hard, almost like 1 in a million almost. 2 in a million nearly. Anyway, that's fine. So 2 in a million. It's a very small number. It's a very small probability. It's what we expect. Not impossible though, but definitely not a large number. By the way, that's in terms of the runs, not the number of spins. Okay, so how many runs are greater than 5 or 10 or 20? Okay, so it's denominated in terms of runs, not in terms of spins of the roulette table. Just an important little remark there. Right, that's it. We'll leave that there.